Hello, and welcome to another SETI Live. I am your host, Beth Johnson, Communication Specialist here at the SETI Institute, and welcome to everybody who's watching. Today, we are going to talk about the kind of incredible results coming in from JWST, looking at the exoplanetary atmosphere of WASP 39b. And I am joined by a group of graduate students and a postdoc who have been working on this research and who are the lead authors on 4 of the 5 new papers coming out. Unfortunately, the 5th person was unable to join us this morning, but we hope she is doing well with all of what is going on for her at the end of her school year. I'm going to bring these guys on one at a time so you can talk to them and meet them and have them talk about their research. But as a quick thing, please let us know where you're watching from. We always love to know where all of our viewers are coming from. And of course, I will give you the shout outs as we go. And we are a 501c3 nonprofit, which means that your donations, your bits, your subs, your stars, your super chats all go to supporting our outreach efforts and keep this program running so that we can bring all of these amazing scientists, early career and late career, to you, and you get to hear them talk about their science. So I am going to bring on the first person, and hopefully we can get our YouTube running. I hope. Okay, let's see. First up, we're going to bring on Adina Feinstein. Adina, hello.
Hi, how are you?
I'm good. Adina is a graduate student at the University of Chicago. She led the paper that is reporting on the transmission spectroscopy of WASP 39b. And she's going to tell us what that is and how it works and what some of their results are. So I know we're going to talk a little bit about what we've seen in the atmosphere as far as some of the chemical constituents, and also some really cool things called clouds on an exoplanet. So Adina, welcome, and tell us more about who you are and what you are doing with these JWST results.
Yeah, thank you. So as Beth said, my name is Adina Feinstein. I'm a 5th-year grad student at the University of Chicago, and I primarily study really young planets, but dip my toe for WASP 39b and sort of older planets here. And so my contribution to this team is leading the NIRISS data reduction. So NIRISS is one of the instruments on JWST. It has a wavelength coverage of around 0.6 to 2.8 microns, so going from the optical kind of into the near infrared. And what's really great about NIRISS is that it has direct wavelength overlap with Hubble, so Hubble Space Telescope. And so we could take previous Hubble observations of WASP 39b and directly compare those to JWST and also improve those with more wavelength coverage. And so what's really great about NIRISS is that it covers multiple water features. So there are about 4 to 5 water bands that we observed in the atmosphere of WASP 39b. Additionally, we found a signature of potassium, which is something that had been hinted at for this planet in previous observations, but was not previously confirmed due to resolution and differences in the instruments. And so now with JWST, we were able to specifically resolve this new potassium feature, which was very exciting. The other thing that we saw for WASP 39 in NIRISS is indications that there's what's called inhomogeneous cloud coverage along the planetary terminator, which I know is a lot of jargon off the bat. So we could break that down a little bit more. The terminator is like the region around the planet that we're observing through. So it's kind of like along the edge there that we're observing. Inhomogeneous clouds basically means patchy clouds. So similar to what you would see here on Earth, where you get some regions with lots of clouds, some regions with no clouds. So kind of different cloud coverages. And so because NIRISS goes into around 2 to 2.8 microns, that wavelength coverage is where we really see this evidence for clouds that HST was not able to see because it didn't observe that far into the near infrared. Mm-hmm. And so it was really exciting to see this. And it was a huge back and forth between the data reducers and the modelers to try to figure out exactly what kind of cloud models would best fit this data. But we're pretty comfortable with the conclusions that we've reached here. And so this is one of the first direct evidences of these kinds of patchy clouds on another planet, which is really exciting.
Okay, so tell us a little about WASP 39b, what kind of planet are we talking about here?
Yeah, so WASP 39b is about Saturn mass planet. So, about 100 Earth masses or so. And then it's a Jupiter in radius. So this tells you that the planet is really heavily inflated, because for something that's a Jupiter in radius, you would expect it to be a Jupiter in mass. But because it's much lower mass than Jupiter, but has the radius, it tells you that its atmosphere is very big. And so this is one of the reasons why we targeted WASP 39b for this program, is because of its inflated, puffy atmosphere. It would be a lot easier to see some of those features than what we might expect for, say, like terrestrial or smaller planets where the atmosphere is much thinner.
Okay, so we have a puffy, hot Saturn, basically.
Yes,
right?
on like a 4-ish day orbital period. So very, very close to its star.
So we're not talking, so when we talk about clouds, we're not necessarily talking about, say, like terrestrial weather patterns, right? We're talking about more, so when you visualize it more, think of like the patchy storms on, say, Jupiter, right? Like the Great Red Spot and all of those. Okay. Yeah. So we're talking more cyclonic clouds, maybe just like differences in the gas composition in various areas.
Yes, it's the same way that you see like the bands on Jupiter in its clouds, right? You see those stripes. Think of something very similar to that.
Okay. And so what did you find in the clouds chemically? I'm sorry if I'm asking you something that you already said. I apologize. I am trying to work out the YouTube issue as well. So what did we find in the clouds, and why is it important? Like, why is this like significant?
Mm-hmm. Yeah, so we found a lot of water in the clouds. So that was good to check off, and Evie will talk more about that for her paper. The other thing that we saw was a little bit of carbon monoxide, and we didn't see any carbon dioxide or any methane, which places kind of an upper limit on carbon-bearing species. So carbon monoxide has a carbon dioxide has a carbon, and methane also has one carbon. So we get a lot of water and not a lot of carbon-bearing species. Together, that tells you what's known as the carbon to oxygen ratio, or the C to O ratio. And you can use that to infer where the planet had originally formed. So the farther you are from your star, the lower your C to O will be. And if you migrate inwards, right, like kind of semi after you formed, you'll retain that low C to O that you formed with. And so that's what it's telling us, that we think that WASP 39b formed very far from its star and moved inwards to the 4-day orbital period that it's at today, rather than forming in its exact location where it is now.
So we're just adding more pieces to the planetary formation, the planetary system formation puzzle, which is not as clear cut as we originally thought it was going to be.
That's right. Yeah, because we can't observe planet formation because it happens on 5 to tens of millions of years, which is not something that anybody here is going to observe, unfortunately. Right. So we can use these kinds of chemical species to infer or make hypotheses about how the planets got to be where they are today.
So how did you become involved in this project?
Yeah, so my advisor, Jacob Bean, is one of the co-Is for the JWST Early Science program. And he approached me in about early January of this year and was like, hey, do you want to do this nearest data reduction? It's a pretty challenging instrument. And I really like programming, so I'm always kind of up for a challenge. And so I took a stab at it, and somehow this paper came out of it. So I consider myself really lucky to have had that opportunity.
There is always an element of luck to scientific research. Like, you have to be the person who gets to see the thing first, really, and sometimes that's luck,
100%. Yeah.
So when you say that you were doing some programming, what sort of algorithms did you create for this? What did you write?
Yeah, so I write primarily in Python. The things that I contributed directly was going from the actual images that JWST will pass down to the transmission spectra, so the kind of bumps and wiggles that you see that tell you what's in the planetary atmosphere. The images that we get from JWST for NEAREST are not very straightforward. the way that they look is across the detector, you spread out across wavelength and also in the y direction. So you get some information that way. And so NIRISS is a curved instrument. So on a grid, pixel grid, you get something that's really curvy. So to extract that is maybe not necessarily trivial. The other thing about NIRISS is that it doesn't have just one kind of order where you get all of your wavelength information. It has three. The third one we don't use. The second one is actually overlapping with the first one. So you get kind of like one arc this way and then one arc kind of underneath. I don't know if this is working, like this.
Okay.
And so they have very different curvatures. They're overlapping, so they potentially contaminate each other at different wavelengths. And then you also get things like cosmic ray impacts and bad pixels that pop up every now and again. So for the challenges of NIRISS was really, getting that curvature down, making sure that that is accurately tracing the images, and dealing with contamination between the two orders and also background. So those are the kinds of algorithms that I developed for the project.
With the early science release program, or early release science, I can never get that right.
Just call it ERS.
Yeah, ERS. With the ERS program, one of the purposes of it is to train people on how to use the data from JWST. So by that, a lot of what you are and the rest of this group are working on will probably be used as foundational sort of research for future JWST studies, because you guys you have created the wheel, right? Like that's the programming that you have done, other people can now use to analyze data similarly, correct?
Yeah, that is one of the purposes of the program.
That is really exciting. How do you feel about that as a grad student, having that be the case for you right now in your career?
I honestly didn't think about it from that perspective until right now. So now I'm like very overwhelmed.
Well, I apologize, but as someone who has gone through sort of grad school and all of that, like that is really exciting, and I am very excited for you. And we will have you back on towards the end when we have to take some audience questions. But for now, I am going to say thank you and let Adina go relax and contemplate the universe now, because I think I've scared her a little.
You sent me into a downward spiral.
Oh no! All right. So Adina, go off camera for a bit. Take a break, and we will have you back closer to the end of the show. So thank you so much for joining us today.
That was great. Thank you.
All right. Next up, we have Zafar Rusumkulov, who is a graduate student at Johns Hopkins University. Zafar was the person who showed the team the very first spectrum of WASP 39b from a lower resolution, and found the CO2 feature less than a week after the data was acquired by JWST. Is that correct?
Less than 24 hours after.
Less than 24 hours. Wow. Oh my gosh. Okay, so tell everybody who you are and what you worked on and your part in this research.
Hi, thanks for the introduction. I'm Zafar. I'm a fourth year PhD student at Johns Hopkins. I study planetary science. I'm interested in exoplanet atmospheres. I'm interested in using telescopes to observe stars and planets. And yeah, I led the NIRSpec PRISM paper. NIRSpec is an instrument aboard JWST, and PRISM is one of the observing modes. It turns out that this mode has the widest wavelength range of all the modes. It gets you from 0.5 microns, which is kind of like green light, out to 5.7-ish microns, which encapsulates a whole host of various chemical features, various hills and bumps and wiggles in the atmosphere, in the spectrum of the atmosphere. So I led that paper. I led one of the analyses of that data set. And we were indeed the first to get a very solid confirmation of carbon dioxide in the atmosphere of this planet.
Okay, so one of the things that it says is you gave the entire spectrum from the NIRSpec instrument from 1 to 5 microns. Even though that was a lower resolution, how did you do this so quickly? I think is the big question for me.
Well, the truth is, I'd spent maybe 3 years working on the code for this, so I was getting ready. I had quite a head start.
So this is like when people ask someone like you know, some musician, like, how does it feel being an overnight success, and they've been working in the business for like, you know, a decade, and right, it's like sort of a similar feel, right? You're like, yeah, I worked really hard for a long time to get here, thanks.
Yeah, the previous project I worked on was like analyzing a data set very similar to this one. So I had a lot of time to prepare and to train.
What did you train on, since JWST, as we all know, took forever to get where it is today, much like many of us? What data did you work on? Where did you get the data from? What were you observing?
Yeah, so this data set was collected, I believe, at a test facility, a NASA test facility, where they actually had the instrument in a cryo-cooled chamber. And so they took it out to space, basically, inside of a vacuum chamber. And then they looked at a little LED light and stared at it for 3 hours. And then that's the data set that I was able to prepare myself on.
That's amazing. I did not know about that. That's really neat. And how did you get involved in the project?
So my advisor, David Singh, he is one of the main collaborators in the early release science program. And I'm his grad student. And so we've been excited about analyzing JWST data for a long time now. So it was a natural connection there.
Oh, that's really neat. I'm very excited for you myself. I definitely have been involved. I've been interested in exoplanets since Kepler, really. Little late bloomer here. But yeah, so that's really fascinating how you got involved and what you've been working on. I'm going to take a quick second and welcome people in, and also welcome to people from YouTube who have run away to other services. Thank you so much for sticking with us. We apologize if for whatever reason YouTube just won't let us talk to it today. Let's see, we've got New Jersey, Louisiana, Germany, welcome, Willkommen. Someone is saying hi to Evie directly. We'll get to that. Canada, New York, California, Poland, welcome. I do not speak any Polish. I am so sorry. Wisconsin, of course you have cheese. It's Wisconsin. Let's see, California, Iowa, more California, lots of color. Bharat. My flag knowledge is terrible, so I'm not sure about that one. I think that's India. Let's see. Thank you to everybody over on Twitch for joining us. More Germany, Portugal. Wow. Okay, welcome from Portugal. My Portuguese is terrible. I'm not even going to try that one. And Sweden. And what's that?
Commiserations to Portugal.
Oh, yeah. And also Sweden. And my Swedish is rusty, and I haven't done it in a long time. So I'm sorry. I'm not. Yeah. All right. Okay. So, Zafar, what does finding the CO2 feature mean for exoplanetary atmospheric science?
So CO2 is a really exciting molecule to be studying because it seems to be not super affected by various atmospheric chemical processes. It's kind of solid. It's kind of stable there, and it's got this gigantic obelisk-like feature at 4 microns. I think of it as a lighthouse. At 4 microns, at this one particular wavelength range, there's like this giant hill of absorption. And so by measuring the height of that peak, we actually get a really good measurement of the overall sort of metal content of an exoplanet's atmosphere. It's like a signpost. It's like something that we can look at for lots of different planets to do like a one-to-one comparison of, like Adina mentioned, their cloud composition, but also their overall abundance of different heavy elements.
So just for the clarification of the audience, when an astrophysicist or planetary scientist or doing exoplanet stuff says metals, they're talking about anything heavier than helium. Because to astrophysicists, there's hydrogen, helium, metals, everything else. Okay, so that means that we can kind of tell, again, sort of like what Adina said, maybe some facts about the origin of the planet, how it formed, what maybe more about the star, right? Does a lot of like what this exoplanetary atmosphere tell us about the star, since we can't get to sort of say cores of things right now? How do we infer from this what the star is made of?
Well, so the stellar component is actually a bit nuanced from the actual duration of the transit. So we measure the transit, right? We measure this at many different wavelengths. If you add up all the wavelengths and get a really precise measurement of the transit stacked over all wavelengths, you actually get a really precise duration of the transit, and that lets you figure out the radius of the star very precisely. So that's a bit of a added bonus, I would say. But I would say the thing I'm most excited about for this data set is the suite of atmospheric chemistry that is enabled by all these molecular detections, like the sulfur dioxide, very informative of photochemical reactions in the upper atmosphere, water, the water to carbon dioxide ratio, that's going to be interesting to look at later. And all of these things together in tandem can tell us about the interior structure and why this planet is so puffy. It's ridiculously puffy. And so we want to figure that out. So getting to the atmosphere is the first step in understanding this planet and the star holistically.
Okay. Well, so what's next for you after this? Are you going to be continuing working on this data for this planet, or are you working on other planets now?
So we have another opportunity to propose for observations with JWST. We had cycle 1 a couple of years ago, and now we're entering cycle 2, where we will all, as a community, propose for a few hours of time on the telescope. And so right now, I'm working on some ideas for proposals to get telescope time for more observations, and then I'm also working on some other observations and some other offshoots of this observation.
Okay, well, good luck, and thank you for joining us today. And again, Zafar will be back on towards the end. So if you have questions for him, please put them in the comments. If you have questions for any of our guests, obviously, please put them in the comments. And we will try to get to as many of them as we can after we've talked to everybody at least once. So Zafar, your turn to go take a break, and we will have you back on in a bit. Thank you so much.
Thank you.
All right. Joining me now is Evie Achar. Did I get it? Did I get it?
Close. Ara.
Aha. Oh, man. Okay. She is a graduate student from the University of Warwick. She led the paper reporting on the transmission spectrum from an instrument called NIRCam, which I'm sure if you are familiar with JWST at all, you have seen all of these MIRI and NIRCam, because that's where a lot of the images come from. Her spectrum features water and carbon dioxide. So you're going to talk to us a little bit more about the carbon-oxygen abundance ratio and more about where the planet formed. But first, before we get to that, tell everybody a little bit more about who you are and what you were working on.
Yeah, I'd love to. Thanks. Yeah, so I'm in the UK, so it's late at night. That's why it's like dark in the back. Well, late at night, it's 6:30. Yeah, so I'm looking at transmission spectroscopy, as like Adina and Zafar already said, and looking at atmospheres, mainly of hot gas giants, not just hot Saturns or Jupiter. So everything's hot and that's gaseous. That's kind of what I'm looking at. And I'm coming actually from the ground-based side. So like my previous work was mainly on ground-based telescope, like using the telescopes in Chile from the European Saturn Observatory. And I'm kind of then got involved in JWST, and that's where I'm at right now. And yeah, I was the lead author of NIRCam instrument, which is, even though it says NIRCam, like near infrared camera, it also has a spectroscopy mode. So that's why we could also look at the spectrum of WASP 39b.
So will you explain for the audience, just so there's some clarity? We keep talking about spectroscopy and spectrum. Will you explain the basics of those two things so that people know like how and what you're looking at?
Yeah. So what we do is, as they've said before as well, we look at this transit, but we look at this transit sort of the planet goes in front of the star, and we look at that in a different wavelength ranges. So we basically take a spectra at each point, and then we create this transit light curves, as we call it, this dip in brightness in the different spectral wavelength ranges. And if there is a molecule in the atmosphere, like the carbon dioxide, that absorbs, that makes the planet appear larger, and so the dip will be larger. And that's kind of when we talk about spectroscopy or transmission spectroscopy. So because the light is transiting through the atmosphere, that's the transmission, and the spectroscopy as in different wavelength ranges. So we're actually talking about spectra instead of like images itself. Yeah.
Mm-hmm. So where you're looking at sort of the effect of the star on the planet's atmosphere. So it's sort of heating up these elements, these molecules that are in the atmosphere, and then they give off infrared light because they are heated up, correct?
They're absorbing the light.
Absorbing the light.
Yeah.
They're absorbing the light, and so it changes their energy state. So that's what we're seeing. Okay. So you found water and carbon dioxide. We've talked a little bit about carbon dioxide, but go ahead and tell us a bit more about your discovery with carbon dioxide and the water in this atmosphere and what that means for this particular exoplanet.
Actually, there's we did not so NIRCam does not go all the way to carbon dioxide. So
okay.
Yeah, I think that was like Natalie's. I think there was maybe she wanted to say something about methane, because methane would have appeared in the NIRCam spectral range, but we did actually not detect it, which was, in my opinion, equally as important as detecting something. So,
okay, well, let's talk about that then. Let's talk about not finding methane, but you did find water, correct?
Yes. Yeah.
Okay, so let's talk first about finding water, and then I want you to talk about a little bit more about not finding methane, because you're right, that is very interesting, and I want to know more about that. So let's start with finding water in the spectrum and what it means.
Yeah, so the water vapor was already known before from the Hubble observations that we had, but it was kind of like a confirmation, and it was also the water detection that we had before was in a different wavelength range. So water has several different features. So by looking at the several different water features, as Adina said, you can then kind of infer the kind of patchiness of clouds, or can infer clouds. So that was why it was important, and also it helped like having the water feature from different instruments. So not just because we detected water vapor, but also because we could calibrate each other's instrument. So because Adina's instrument, NIRSOS, in her paper, they found water, and it overlaid with exactly with the feature we saw in NIRCam. We were like, okay, this is working great. This is fantastic, right? So that was already like, that is fantastic. All of these like just work perfectly together. And then there was the methane thing, which coming back to this like carbon oxygen ratio. So the methane kind of infers as well that there's less carbon bearing species that we expected. So that's kind of the information, like we would have seen methane if there was a higher carbon to oxygen ratio. So that was basically the missing of it was information for us.
And why are we expecting to find methane? What's the reasoning behind that?
It's kind of it comes from the modeling. So probably Xiaomi can then talk more about the exactly the like modeling and how everything comes to place. But this is kind of the idea of like because it's one of these abundance, like carbon and hydrogen is very abundant, and it's very likely to form the methane. But if it's way less carbon than we expected, it's not as likely to form methane. So that's where then the carbon to oxygen ratio becomes lower.
Okay.
Makes sense.
Yeah, makes sense. So how did you become involved in working on this project? You said you started with ground-based observations. So how did you end up sort of switching over to space-based observations?
Yeah, I had a kind of different approach than everyone else. So it started kind of last year in summer, so 2021. There was just a hackathon for us, the ERS organized a hackathon. So about just like sitting together and developing these tools and looking into, okay, what can we expect the data to look like? What tools do we need to develop to tackle this data analysis and reduction? And so my advisor kind of said, maybe you want to like look into this. JWST is going to become important. Like just get started and get involved. And then I started working on this pipeline with mainly with like some collaborators from the US and from Germany as well. And I got involved in like a pipeline work, and that's basically how I got involved in ERS. It's with pipeline work, and then got asked to lead the NEOChem observations.
That's fantastic. Do you feel overwhelmed? Have I created existential dread in you as well?
No, I think I had some time to get over it. I think since you mentioned it to Adina. No, I really feel like really privileged and like so lucky to be be there at this place, to be able to reduce the data and having the experience to do it when the data came down. That was, yeah, it was definitely a privilege, and I'm very lucky to do that.
I have to admit, when Natalie sent me, so for those of you who have not read the description or do not know who I'm talking about, Natalie Battalia is one of the leading exoplanetary scientists ever. And she was basically the PI for Kepler, and she's amazing and I adore her. And so I asked her to come talk about this paper, and she said, that's great, but I want you to talk to all of the people who led the papers, who are graduate students and postdocs. And so for me, when she said that, I was absolutely in, because with all of the waiting that we all had to do for JWST and all of the careers that were put on hold or had to change directions because the thing that you thought you were going to be researching is not in orbit yet, to see that all of you in these early career stages are getting to work on this data already and getting your names out there, this is fantastic. And I personally am just excited for all of you. So congratulations on this discovery and on this paper and all of this. So,
and big shout out to Natalie. I feel like she was our biggest cheerleader in all of this.
And that's really, Natalie is really wonderful. She was part of the SETI Institute for it. She was also part of my alma mater, San Jose State. So I'm very excited for her and for all of you. So Evie, I am going to bring on Xiaomi to talk some more about some of the photochemistry, and I will have you back on. I have questions for you as a group, so just kick back, relax, and thank you once again for joining us today.
Thank you.
All right, last but definitely not least, Xiaomi Sai, a postdoc at the University of California, Riverside. Xiaomi showed that the sulfur dioxide feature can only be explained by photochemistry. And this is really cool, guys. Really, really, really cool. So, Xiaomi, tell us who you are, what you have worked on, and then we're going to get into some of this amazing science.
Hi, yeah, I'm Xiaomi Sai. I'm a postdoc at UC Riverside. My research interests are mainly modeling planetary atmospheres, especially their chemical makeups of these atmospheres. So my role is a little different. I don't directly put my hands on observational data. I use computer simulations to see what chemical abundances we are expecting for these atmospheres. And for this project, my main contribution is to explain the origin of this sulfur dioxide, SO2. Why is it there, and what does it mean to see these chemical species?
Okay, so let's start with the detection of sulfur dioxide. Why is this important? What was exciting about this particular discovery?
Right, so this feature, this molecular feature, is seen by the NIRSPEC instruments led by Sulfur and Evie. So once we saw that, I think it blew everyone's mind, because we didn't expect to see that. This is a hydrogen-rich, hydrogen-dominated atmosphere. And in this environment, the most chemically stable molecule would be hydrogen sulfide. So it's analogous of water. So if you remember, water molecule is H2O, 2 hydrogen, 1 oxygen, and you replace the oxygen with sulfur. Sulfur actually sits right below oxygen in the periodic table. So that's the stable molecule we would expect. But sulfur, hydrogen sulfide is very reactive to some photochemical products, i.e., when you have high energetic stellar light shine on these atmospheres, it will produce some, we call those chemical radicals that will trigger some important chemical reactions. So H2S will react with this with these radicals and eventually form being converted to the more oxidized form SO2. And this is important because this is arguably the first time we see a solid evidence of photochemistry in play for an atmospheres beyond our solar system.
So this is sort of an analogous process to, say, creating the ozone layer here on Earth, right? So we have the solar energy coming in and affecting molecules in the atmosphere, and rather than creating, say, sulfur dioxide, ours breaks it up and we end up with O3 molecules, which is what ozone is. And thank goodness, because we need the ozone to survive the heat of our sun. Yay, all that UV radiation. So what is next on figuring this out, and what does it say? I think most importantly, what does it say about this particular planet and its formation, its existence right now?
Right. So we've talked about how the heavy elements, that's everything heavier than hydrogen and helium, can tell us about the formation condition of these gas giants. And we can also draw the connections to Jupiter and Saturn in our own solar system. So we talked about this carbon to oxygen ratio. So in addition to that, when we see sulfur and we have some ideas of how much sulfur is in this planet, we can also gives us another tracer for the formation history, because if you think about the disk that gave birth to these planets, you have we call this, we have a beautiful name for this snow line, because these volatiles will condense in different locations. So water will condense first and then carbon dioxide next. So that's why you have different carbon to oxygen ratios, right? Because when you first condense water, then most of the oxygen will go into the icy components. But opposed different from that, sulfur actually, most of the sulfur will stay in the refractory form. So it's relatively more uniform compared to oxygen and carbon. So that could give us a reference of the formation condition to that. And secondly, we also found SO2 molecule is quite sensitive to the enhancement of heavy elements. So if you have, say, 5 times of the solar metallicity, or if you have 10 times, or if you have 20 times, we will see very different SO2 feature. So that can give us a very tight constraint on this atmosphere property. So that's very useful.
Wow. Okay. So this one molecule tells us a lot about this particular exoplanet, its atmosphere, and even its star.
Yeah.
And its formation. So that is a lot of weight to rest on one particular molecule, but that's a very exciting discovery. So how did you end up involved in this research?
Yeah, so I got involved the latest. I'm the latest to join the party. So I was approached after people figured out that that small bump right before the CO2 features that I talked about. It's around 4 micron, and SO2 is the perfect candidate to explain that spectral feature. So after that discovery, I was brought in to lead a team. I think I did a work on a different planet, a smaller planet, but with a similar temperature conditions as WASP for the 39b. And I also my model also predicted that sulfur SO2 feature for that planet. So my role would be, this is different from the observational team. We didn't really prepare for the whole modeling team, but we managed to assemble a team with independent photochemical models to simulate the atmosphere of this WASP-39b, and every model independently confirmed the production of SO2 more or less consistently. So that gave us really quite good confidence of we understand the underlying physical and chemical processes of these chemical profiles we have observed.
Okay, so again, learning a lot about a planet from one molecule, and that is fantastic. Okay, I'm gonna thank you, Xiaomi. I'm gonna bring everybody back on, and audience questions would be great to have about now. So if you've got any about WASP-39b and all of that, that would be fantastic. And I'm gonna welcome everybody back and do a little rearranging of the screen. Oof. Nah, I don't like that. Okay, we'll just stick with this. And
my light was automatically switched off because it's after working hours.
But it really showed off the sweater. So
right? Yeah, it was great.
Yeah, it was great. So thank you everybody again for joining us. I would like to ask sort of each one of you, what was the most surprising or interesting thing about your research that you found or learned? It doesn't have to necessarily be about the planet itself, but about a research technique or anything like that. I really want to know like what this was like for all of you to work on. So I'm gonna start with Xiaomi, since you were last up. So what's the most interesting or unusual thing that you found?
Oh, definitely sulfur dioxide in this case. Have to give it to that, because like this has been mentioned, we are still trying to figure out the abundance of methane, water, and carbon dioxide. This seems to me like a very, very huge leap. We suddenly can also see sulfur, because sulfur is less abundant than carbon and oxygen, and we also see how it's converting from the more reduced form to a more oxidized form driven by photochemistry. And now we've observed the photochemical processes similar to what we have on Earth, like you said, to produce ozone from oxygen. And this is probably being overused, but this really opened a new window to observe for smaller planets, because, for example, sulfur records actually told us a lot about the oxygen evolution on Earth itself. So this really is, I'm very optimistic about the future for characterizing these exoplanet atmospheres.
So that actually answered what was going to be my second question. So I'm now going to make everybody do this. So Zafar, what was the most interesting or surprising thing that you found out, and what are you looking forward to working on with this project or in the future? Any sort of research you're excited about?
For me, the most interesting thing was actually buried deep in our paper. We looked at the time of transit of the planet. So we looked at the positional offset of the light curve in time. And with this level of precision, you can get it, you can see the signature very clearly, that it looks like one side of the atmosphere is a little bit different from the other side. So when the planet passes from the star, the morning side and the sunrise side and the sunset side have slightly different chemical composition. And so we were able to see the signature faintly, but it's there. And so hopefully we can learn something interesting about the weather and circulation patterns in the atmosphere of the planet. Regarding the future, I'm just really happy that JWST is performing so well. The data sets have been fantastic. The things that we were worried about, I think we were just being cautiously pessimistic. Things are looking great. And for the most part, I'm really excited to see what data comes out soon.
Fantastic. Thank you. Evie, how about you?
Yeah, I kind of want to build on what Zafar was saying of like, yeah, I think because we simulated the data before and we were like, okay, what can we expect? And I think actually we simulated it worse than it turned out to be. So I was surprised on how clean the like gas was, and because it was such a big effort in terms of we got the data and then everyone just like basically didn't talk with each other for like a week, and then we compared our results. So we did independent reductions, and I think it was one of the like best moments was just like seeing everyone's results and comparing them and plotting them and seeing what everyone else got, and it just agreed so well. That was like one of the best moments, and just showing them to everyone and showing like, hey, every reduction can see the same thing. It's so beautiful that was, I think, both the biggest surprise, but also, I don't know, the most optimistic way of like, we can now like, we're like, oh, it's performing so well, we can do the science we want to do, and that is like what I'm looking most forward to, is like how far can we push it, and being excited about the things we don't know we're going to be excited like in 5 years time stuff. That's
yeah, I can see how that would be, and I have to admit, like, watching this data, watching the analysis of this data come back in, as a journalist, as someone who gets to ask you guys all these questions, it's very exciting to me as well. When this press release, or rather these 10 press releases, crossed my email, I was very excited, and I'm really glad I've gotten to speak with all of you about it. Adina, of course, last but again not least, how about you? What was surprising, exciting, interesting, and what are you looking forward to in the future?
Yeah, so I think the most surprising part for me was, well, first it was everything, because this is my like first kind of toe in the water for atmospheric sciences. So that was new. I like had to learn a lot along the way, which was all very exciting. But for me, I think there was a lot of hesitancy among the exoplanet community about using NIRISS, or the instrument that I led, for exoplanet science, because the layout of the detector is so challenging that there was a lot of hesitancy and a lot of back and forth on the believability of the data. And at the end of the day, you know, much like Evie's and Safar's papers, we had multiple teams reducing the data. All of the spectra looked the same. And we were able to convince modelers and the rest of the community that it's a great instrument to use. So I'm really looking forward to seeing what proposals come out of cycle 2 that use NIRISS, because it's not as scary as it seems originally. I would also say, yeah.
I think people are going to have you to thank for making it a lot less scary. So again, to add to your existential dread, there you go.
I think so it's not just me, it's also the 5 other people who reduced the data, including Zafar. So thank him too.
So kind of a question for the group. This was a very big collaborative project. You know, again, there are 5 papers that came out of this with 5 separate lead authors. Natalie Battalia was coordinating a lot of it. The press releases had quotes from multiple people. What was it like for you to work on this sort of huge project? Did you feel isolated from other people, or did you feel that it was very collaborative? Was it helpful to have so many people? I mean, Evie kind of addressed this a bit, of, you know, being able to like reduce your data and see that other people agreed with you. So, hey, validation. But like, what was it like being involved in this? Like, if you could give me like a 1-sentence or 2-sentence description of what it was like working in this collaboration, what was it like? And I'm going to start with Adina. I'm going to kind of go in a different order now.
Let's see, a 1-sentence summary, I would say it was a really wonderful experience to have all the expertise that we needed to go from data reduction to results in the span of like 4 months. But it was also extremely stressful. I mean, we were all working to hit a deadline of getting these results up before cycle 2 call for proposals, so that our results would be useful to the community. And so it was a huge, huge time crunch. So great, but stressful.
That sounds about right. Evie?
Yeah. Yes. It was very stressful. Yeah, so it's been yeah, I kind of want to like think like all the like we had kind of like a core team that was like the kind of like mentor Kevin Stevenson, and then we have a data analysis lead Megan Mansfield and a modeling lead Sarah Moran. So we had like specific kind of like as like people that lead separate parts, and it's and I've worked with so many people that I haven't really interacted with before. So it's been just a huge growing experience as a researcher as well, to be able also to pick everyone's brains, that you just all combined and connected. And it was, yeah, a lot, but also amazing.
Fabulous. I'm very happy for you. Zafar?
I have a little anecdote to share. So
Sure.
when the near spec prism spectrum actually arrived, it appeared on my laptop, and I happened to be surrounded by a group of respected colleagues and mentors and researchers at UC Santa Cruz. And so there was a moment where there was a bunch of people sitting next to me, and we all saw the spectrum basically at the same time. And so everyone was so excited, and we saw the carbon feature pop out, and we saw the sulfur dioxide feature. We didn't know what it was at first. So it was like, I felt like a movie scientist, having all these people like all hustling and bustling around. So it was special. It was cool to share this moment of discovery with so many of our friends and colleagues. It was a good time.
That is awesome, and I'm a teensy bit envious. Xiaomi, how about you?
Definitely both stressful and exciting at the same time, because we have to deliver this this results in a very quick turnaround. But I would say, as a modeler who comes in an angle of trying to explain the feature, the spectra from a theoretical basis, I definitely feel privileged to be able to experience the thrill of discovery, because it's very rare for people like me. I'm actually in Zafar's anecdote, because on that day that this group of people were seeing that spectra, I was also visiting Santa Cruz for a summer program there, but I chose to go to the beach on that day, and I think I missed that moment. So that's if I can go back in time, that's the one thing I would change.
Oh no. Well, but you got to go to the beach. So I mean, oh, I feel for you. Well, everybody, thank you so much for joining me today. We got this kind of scheduled really quickly and really well, for the fact that you are all scattered all over the place, including over in the UK. So Evie, thank you so much for working late this evening to be here. We all appreciate it, and I know our audience appreciates it. I am excited to see what all of you do in your careers, and I completely expect to have all of you back at some point in time to talk about whatever your next endeavor, your next research is. So definitely keep in touch. Let me know how things are going. For those of you who do have some sort of public-facing social media, I believe that's Evie, did you want to share where people can find you at?
Sure. Mostly on Twitter. So if you go Evie and then underscore and then my last name R, that's mainly me.
All right, Adina.
Yeah, I'm also on Twitter for Feinstein20. So.
Okay, Xiaomi.
Also Twitter, Xiaomi Sai, I think. I'm not entirely sure.
We don't use our own names very often, so it's
Yeah.
like, wait, what? Yeah, I understand. And so far, I know you don't have forward-facing social media, but you know, if you ever do, please let me know. And absolutely, everybody keep in touch and let us know how your research goes. I'm very excited for all of you. And I will let you get back to your end of semester lives and getting ready for the holidays. And thank you for the wonderful, wonderful, ugly holiday sweater party that you have given me today. You have really made my day. So Merry Christmas and Happy Hanukkah. And all of you have a wonderful end of year.
Thank you very much.
Thanks so much.
Thank you, everybody, for watching. We'll see you next week on Tuesday for a special SETI Live to talk about, and you are all going to be so excited, UAPs. And I will be talking with Anna Maria Barea, who is on the new NASA UAP committee. So come join us. I promise I will take the topic very seriously and treat it scientifically. So come join us. So thank you everybody for watching, and have a fabulous rest of the week.